Okay. Hello everyone. Let us see the properties and theorems of Laplace transform. In amplitude scaling, if the amplitude or the magnitude of a time domain signal is multiplied by a constant A, then its Laplace transform is also multiplied by the same constant. Let me prove it. The proof says, by definition of Laplace transform, we know that x of s is equal to Laplace transform of the signal x of t, which is equal to integral from minus infinity to plus infinity x of t into e power minus st dt. Everybody knows about it. So if you asked me to find out Laplace transform of the signal whose magnitude or amplitude is multiplied by a constant a, will be obtained by a into x of t e power minus st dt. So what will happen? This is equal to a into integral minus infinity plus infinity x of t into e power minus st dt. We know that this integration refers to x of s. So this is a into x of s. So Laplace transform of a signal whose magnitude is multiplied by a constant is given by a into x of s. Right? Next property. Let's see about linearity property. Linearity property. The linearity property states that Laplace transform of a weighted sum of two or more than two signals is equal to similar weighted sum of Laplace transforms of individual signals. If you know the Laplace transform of x1 of t is equal to x1 of s, and the Laplace transform of x2 of t is equal to x2 of s, then Laplace transform of weighted sum of those two signals a1 times of x1 of t, weighted sum of those two signals is given by similar weighted sum of Laplace transforms. So a1 times of x1 of s plus a2 times of x2 of s. How to prove this? I hope this is very easy. The proof is really very easy. The proof. The proof says, by definition of Laplace transform, x1 of s is obtained by making transformation of x1 of t. This is given by minus infinity plus infinity x1 of t e power minus st dt. Similarly, x2 of s is equal to Laplace transform of x2 of t, which is equal to integral minus infinity plus infinity x2 of t into e power minus st dt. Okay. Now the Laplace transform of the weighted sum of two signals is equal to similar weighted sum of Laplace transforms. Let's see. a1 times of x1 of t plus a2 times of x2 of t. How to pronounce that? This is equal to integral minus infinity plus infinity a1 times of x1 of t plus a2 times of x2 of t. Both are weighted sum. Actually, it into e power minus st dt. Okay. The signal for which you want to take the transform multiplied by e power minus st, and if it is integrated with respect to minus infinity plus infinity, you are obtaining its Laplace transform. So let's see. The result says it can be decomposed into a1 times of integral minus infinity plus infinity x1 of t into e power minus st dt plus a2 times of integral minus infinity plus infinity x2 of t into e power minus st dt. So this particular portion, you know that this refers to x1 of s and this refers to x2 of s, because we have seen just before few minutes. So it results in a1 times of x1 of s plus a2 times of x2 of s. Okay, so Laplace transform of weighted sum of two or more signals is equal to similar weighted sum of individual Laplace transforms. Okay. Let's see what this can be done for time differentiation. Time differentiation property states that if a causal signal is piecewise continuous, two assumptions we have made: x of t is causal and it is piecewise continuous, right? Laplace transform of x of t is equal to x of s. Then what is the Laplace transform of differentiated version, its derivative with respect to time, is equal to s into x of s minus x of 0. Look at that, Laplace transform is multiplied by the factor s and the initial value is subtracted from the result of the product. Okay? Initial value of x of t. This x of s refers to Laplace transform of x of t. Okay, let's see the proof. How to prove it? Okay, proof. By definition of Laplace transform of a causal signal, how to obtain it? X of s is equal to Laplace transform of x of t, which is given by integral 0 to infinity, because we have taken this as causal, starts from 0 onwards, e power minus st dt. So when I apply Laplace transform on the differentiated version, it says it is equal to integral 0 to infinity, the given signal is d by dt of x of t. Yes, it is to be multiplied by e power minus st dt. Or even we can even shuffle this to identify which is to be treated as u, which is to be treated as v, so that you will find out integral uv is available here, e power minus st d by dt of x of t dt. This is grouped together. Okay, I just want to remind you, integral uv, if it is present in any problem, u integral v minus integral of within braces du integral v is to be taken as a factor, du multiplied by integral v. So integral v is essential. Integral v will be multiplied by u once, integral v is multiplied by du once. If I fix in this problem u is equal to e power minus st and v is equal to d by dt of x of t. Okay. So let me go back to this problem. Laplace transform of d by dt of x of t is equal to integral, it is to be, it actually what was available, integral 0 to infinity e power minus st d by dt of x of t dt. Yes, it is to be treated like this. So the first portion is e power minus st multiplied by the integral of v. So if it is integrated, you know integral v is equal to simply x of t, e power minus st into x of t. Agreed? Where the lower limit is 0 and upper limit is infinity, minus integral starts from 0 to infinity. Here this term, this one will be differentiated once. When I start differentiating it, this will become s into e power minus st. Okay, now multiplied by x of t. This is to be treated as such dt. Could you identify that? How many terms are there? E power minus st x of t, minus s into e power minus s of t into x of t dt. Okay, so let me find out the Laplace transform of time differentiated signal, causal signal, which is piecewise continuous, will be given by, so the first term, which is e power minus st into x of t, where the lower limit is 0 and upper limit is infinity, where the second integral 0 to infinity minus s into e power minus st dt multiplied by x of t dt. Okay, now let me take this infinity upper limit minus lower limit. Okay, what will happen? E power minus infinity into x of infinity minus e power 0 into x of 0. Agree? Whereas about this integration, when you start taking minus s outside, it will become plus s integral 0 to infinity x of t into e power minus st dt. Did you notice? This portion can be very well identified as x of s. So s into x of s is readily available. E power minus infinity is 0. So e power 0 is 1. When you start substituting those, e power minus infinity is equal to 0 and e power 0 is equal to 1. The Laplace transform of the signal d by d, differentiated derivative version of a causal piecewise signal, will be given by s into x of s minus the left out term, only x of 0, initial value. So this is the proof or the statement. If Laplace transform of x of t is known to you, which is Laplace transform of x of t is given as x of s, isn't it? So Laplace transform of d by dt of x of t is given by s into x of s minus x of 0, initial value. The signal is to be known. Okay, let me go to the next property, time integration. How to apply this property? First of all, what is this property? This property states that if a causal signal x of t is continuous, Laplace transform of x of t is x of s is known to me, then the Laplace transform of integral x of t dt, if x of t is continuous and causal, integral x of t dt, isn't it? What is the signal? This is, it is passed through an integrator, integrated. The output of an integrator is to be now Laplace transformed. What is the answer? It could be easily obtained if you know the answer for Laplace transform of a simple signal x of t. If you know x of s divided by s, and if you know the signal, integrate it and evaluate the result of integration at t is equal to 0, and also it is to be normalized by a factor of s. So let me see how to prove this. The proof is a little bit tough to see. I'll show you that. X of s, which is equal to, by, let me call this as proof by definition of Laplace transform. Laplace transform of a causal signal is given by x of s is equal to Laplace transform of x of t, which is given by integral 0 to infinity x of t into e power minus st dt. Right? Now we don't have x of t directly. We are supposed to apply the x of t through an integrator. The output of an integrator is to be now transformed using Laplace transform. Output of an integrator is called as, right, integral x of t dt, for which I need to apply Laplace transform. Whatever it may be, integral is from 0 to infinity. What is available as a signal with you right now is only the integrated version, and you have to multiply it by e power minus st dt. Again there comes integral uv. u into integral v minus integration of, let me use du multiplied by integral v is to be put up as a common under this integration. Agreed? So what is u, what is v in our case? U is equal to integral x of t dt, and v is equal to e power minus st. So using these two assumptions into the formula, let me find out Laplace transform of the integration result of a causal signal, continuous signal. So let me find out the answer. Is given by, let me put this, uv, u is integral x of t dt, uv, what is v? E power minus st divided by minus s, where the lower limit is 0 and upper limit is infinity. The next factor, under integration, you have to use differentiated version of u, and then you have to take this integral v. Differentiated version of u, integral x of t dt, if it is differentiated once, you will obviously get x of t, there is no doubt, e power minus st divided by minus s dt. Right. Now let me find out the answer. So integral x of t dt is the first factor, and it is to be evaluated, substituted with infinity, t is equal to infinity. Integral is to be substituted with upper limit, where the upper limit on the next factor will be e power minus infinity divided by minus s minus. Now you can notice that if you take the second part as, again, integral x of t dt is to be treated as u, and yes, e power minus st as v, you can find out. First of all, let me complete the upper limit and lower limit, isn't it? So integral x of t dt, where t is to be substituted as 0, e power minus infinity now becomes e power 0 by minus s. So this is with upper limit and this is with lower limit, right? Whereas the next term will simply become 1 by s minus s. If it is taken outside, it will become 1 by s integral 0 to infinity, causal signal, continuous time signal. So x of t into e power minus st dt. Everybody knows that this refers to simply x of s alone, x of s divided by s. Whereas there comes only doubt on these two values. E power minus infinity 0. If this is 0, then I don't have to even, e power minus infinity is 0. So the entire term will become 0. E power 0 will become 1. If this is 1, you can find out that this is equal to the term. E power 0 is 1. Let me write the final answer. Laplace transform of the result of integration x of t dt is given by 1 by s integral x of t dt, where the lower limit value is t is equal to 0. Whereas for the second factor, you have 1 by s integral 0 to infinity x of t into e power minus st dt. Of course, the answer for one term is x of s by s. Second term will become integral x of t dt integrated once and divided by the factor as s. But the condition is the integration is to be substituted with the value of t is equal to 0. Okay. With this, let me stop the first phase. Whereas, let me move on to the second phase in a couple of minutes.